After learning about vertex form of a quadratic function in the previous section, we're now going to transition into a second form in which quadratic equations can be expressed, and that is called standard form of a quadratic function. Ultimately, what standard form is that your y value is going to be equal to some number a times your input variable x squared plus another number b times x plus c. So really you kind of have separate terms for your x squared term and your x, and then a constant there whenever we're dealing with standard form. So we're going to work to graph these quadratic functions, which will ultimately make parabolas when the equation is expressed in standard form. So to identify some of those characteristics of the graph when we're dealing with an equation in standard form, one important thing to acknowledge is when the graph is going to open up versus when it is going to open down. And it does turn out that the graph will open up whenever your a value is greater than 0, and then whenever your a value is less than 0, it will open down. So the a value in this particular case is just only the number that times with the x squared term only. So it's kind of a nice, easy way to know if your parabola opens down versus if it opens up. And then also very similar to what we've seen previously, your graph is going to be vertically stretched, so skinnier than kind of normal, whenever your absolute value of a is going to be greater than 1. So that's when you have positive numbers larger than 1, or when you have negative numbers less than -1, of course. And then your graph will be vertically compressed, so in other words, a little bit wider than normal, whenever your absolute value of a is less than 1. So again, that equivalently means that your a value is going to be smushed somewhere between -1 and 1, just as long as a is not equal to 0. So that's kind of the same thing as we've seen before. And then also a y-intercept is going to be the same no matter what sort of function we're dealing with, because a y-intercept always is going to be having a 0 for an x coordinate, so you'll be able to substitute that in. But it turns out that for standard form, something kind of interesting kind of always happens, because if you think about plugging in 0 for x into that equation, you're going to have a times 0 squared plus b times 0, which means that those terms right there are just going to be zeros and then plus c. So then it just turns out that the y is going to be a c. So actually when we're dealing with standard form, actually the c value is actually going to be the number where it crosses through the y-axis at. So that's something that's kind of unique to standard form, and we'll see that in the examples that we see a little bit later on. So those aspects and those elements really aren't any different than we've seen before. The last elements of the graphs of quadratic functions that we want to be able to identify whenever the equation is expressed in standard form is that of the axis of symmetry, as well as where the vertex of the parabola is located. Now, when I tell you where the axis of symmetry is going to be identified when the equation is in standard form, it's going to seem like it just kind of comes out of nowhere, and you'll wonder, like, why is it always that? And we don't have enough tools in our toolkit to be able to explain why that is quite yet. We will get there, and you'll see later on how it all fits together and why it makes sense as it does. So I'm just going to tell you right now that the axis of symmetry for a parabola, when the equation is expressed in standard form, is going to be the vertical line x equals, and here's what it will be, is it will be -b over 2 times a. So you have to recognize that b is going to correspond to that number b right there. That's the coefficient of your x term. So we have the negative in front of it, of course. And then that a corresponds to the number that's timesing with the x squared right there. So like I said, this axis of symmetry right here is kind of coming out of thin air right now. So later on, we will see exactly why it is always -b over 2a. Now, this is something that is unique to when it's in standard form. So we don't use -b over 2a when your equation is in vertex form or in other forms. It's just something specific to this form right here in standard form. So then to be able to identify the vertex from there, it actually does turn out that the vertex is going to have the actual same x-coordinate as the axis of symmetry, of course, because we know that the vertex is right on the axis of symmetry, And so then to determine the y value of where the vertex is at, you can just plug in whatever negative b over 2a is as a number into the equation and determine that. So like if your parabola equation was like f of x, then you would just do f of negative b over 2a, basically just plugging negative b over 2a in for x to find that particular y value. So that'll make sense in just a little bit right here as we kind of find some aspects of quadratic functions here. So before we actually do the graphing here, we want to be able to identify some characteristics of the graph just kind of from the equations here. So it does say to identify each of the following characteristics of the graphs of each quadratic function. You're going to see with both of these examples that I have right here that they are both quadratic equations and also expressed in standard form because you have separate x squared and x in constant terms in each of these. So we'll take a look at this first example here. So we're going to try to identify just the three things that are labeled towards the bottom of that box there, the axis of symmetry, as well as the vertex, as well as the y-intercept. So the axis of symmetry is always going to be located at x equals negative b over 2a when your equation is in standard form like it is right here. So we do need to acknowledge and recognize then like what A actually is, what B actually is, and what C actually is. So I'm going to acknowledge the fact that A in this case is negative 1, because that's the number that times is with the x squared terms. B is going to be a positive 10, and then C is always going to be the constant term, which in this case is, sorry, not 10, it's a 1 there. Alright, so to find the axis of symmetry in this particular one, the axis of symmetry is going to be negative of your B value, so negative of positive 10, over 2 times your A value, which is 2 times negative 1. So if you do simplify that, you get negative 10 divided by negative 2, which equals positive 5. So that does mean the parabola is going to have an axis of symmetry with the vertical line of x equals 5. So then you'll know that the vertex, the tip of your parabola, is going to have that same x coordinate of 5. And then you can just plug in that 5 into the equation to find the corresponding y value. So if you do negative of 5 squared plus 10 times 5 plus 1, that's going to equal the corresponding y value. So if you simplify that, you get negative 25 plus 50 plus 1, and then go from left to right. So you get positive 25 plus 1, and that's going to give you a final result then of 26. So right there, the ordered pair 5, 26 is going to be where the vertex of this quadratic function or this parabola is going to be located at. And then finally, the y-intercept. So any y-intercept, of course, is going to have a 0 x coordinate, so you can just substitute in a 0 for x. Pretty simple with this one, because of course then it's really just going to zero out those first couple of terms, so then you just get y equals 1. So like I said, when your equation's in standard form, it just turns out that that c value actually is always going to be the y-intercept. And then just one more example, finding the same sorts of stuff. So the axis of symmetry is going to be the equation of x equals negative b over 2a. So acknowledging that a is negative 4, actually b is negative 4, and then c is negative 2 in this one, then negative b over 2a is going to be negative of negative 4, because that's your b, and then over 2 times a, so that negative 4 is coming from the a value there, and we simplify this, we're going to get positive 4 on top over negative 8 on bottom, so that does amount to be a negative 1/2. So your axis of symmetry is going to be the line x equals negative 1/2. So then the vertex of your parabola will of course also have that same x coordinate of negative 1/2. So then we can plug in negative 1/2 in for x to find the corresponding y value. So if we found f of negative 1/2, we would need to do negative 4, and then times negative 1/2 squared minus 4 times negative 1/2, and then minus 2. So doing the exponent part first, if you do negative 1/2 squared, or negative 1/2 times negative 1/2, you get positive 1/4. We can multiply those two together right there, so it's a negative times a negative, it'll turn to a positive, which will be 4/2, but 4/2 is actually 2. And then if you do multiply the negative 4 and the 1/4 right there, you're going to get a negative 1. So really just have negative 1 plus 2 minus 2, which is positive 1 minus 2. which gives you ultimately, finally there, -1. So it does turn out that -1/2, -1 is going to be the location of the vertex of your parabola. And then finally, for the y-intercept of this, you can plug in a 0 in for x and then solve from there. So f of 0 is actually, of course, just going to equal -2. So that would be where your y-intercept for this is going to be located.